Perfect. Okay. Good morning, everyone, and welcome to today's session of the WST Time Domain talk series. Today's speaker is Dr. Zdenek Prudil. I'm very honored to have him with us today. Zdenek obtained his PhD in 2020 at Heidelberg University, and in 2022 he was awarded the fellowship from the European Southern Observatory and moved to Garching. Today, he will speak about RR Lyrae variable stars in the galactic bulge. Thank you, Zdenek, for being with us today. The floor is yours.
Hello, everyone, and thank you for giving me the opportunity to present my work and my ideas. Today, I'm going to talk about RR stars, the pulsating variable stars in the galactic bulge, therefore in the central region of our own galaxy. Now, why should you sort of care about the galactic bulge and the galactic bar that is located inside the central region of the Milky Way? It is the closest bulge or central region where we can resolve individual stars, all evolutionary stages. The next similar region like this is in the Andromeda Galaxy, which is more than 100 times further away. And our Milky Way bulge harbors several populations with different star formation histories that can be associated with different substructures in the bulge, like the galactic bar. Now, the galactic bar is going to be actually the main point of this talk because it's a very prominent structure in the central region of the Milky Way. It harbors approximately half, 2/3 of the stellar mass in the galactic bulge. It has a strong influence on the Milky Way halo, especially on the stellar streams that are located there. And it acts as a redistributor of gas from the outer regions to the central regions of the Milky Way, and it's likely responsible for the formation of the nuclear star disk. Now, to sort of divide, sort of categorize the bulges, we divide them into two sort of categories: the boxy X-shaped bulges, where the dominant feature is the galactic bar. They have the sort of peanut shape feature, and they origin from the instabilities in the disk early on, and they're characterized by cylindrical rotation. While sort of the other bulges, the classical bulges, they have a formation mechanism that comes from the mergers, where sort of a dwarf galaxy or some other object sort of merges with the galaxy and forms this sort of elliptical or spherical structure in the center of the galaxy. These classical bulges share similar properties to elliptical galaxies, particularly the random motion of the objects inside these bulges. Now, for the Milky Way in particular, people have been trying to study the galactic bulge using classical pulsators and different standard candles to sort of understand the structure and to describe and characterize the Milky Way bar that we have there. One of the most used objects for these or standard candles are red clump stars, which sort of fall into the intermediate age category of stellar tracers. And they've been successfully used by Gonzalez and collaborators and Beck and Gerhardt to sort of trace the Milky Way bar, to characterize its angle and shape and size. Another kind of tracer that was successfully used to sort of trace the Milky Way bar are Lyrae variables. They sort of cover a broad range of ages, from intermediate age from a couple gigayears to, let's say, 11, 12 gigayears. And in work, for example, by Grady and collaborators back in 2020, they found that the intermediate age Lyraes actually do trace, or in their spatial distribution, you can clearly see the Milky Way bar. But while you move to the older population Lyraes, that's where the barred structure sort of disappears. So another kind of tracer that people use to study the galactic bulge are RR stars. And they've been also used extensively to search for the barred distribution in their spatial properties with a sort of a discrepant results in principle. And I had a paper on this spatial analysis side last year, but this is not going to be that much of a title or topic of this talk. We're going to be focusing more on the dynamical side in this talk. And this is not the only work on RR stars. There has been a plethora of papers that focus both on the spatial and dynamical side and try to sort of characterize the RR spatial distribution in the galactic bulge and try to search for any sign of bar distribution in their population. This is particularly important because then it can help you to time the bar formation or the bar evolution with respect to the sort of older population. Now, some papers claim to see the Milky Way bar in the spatial distribution of irregular stars, while others didn't. So there's a lot of caveats, a lot of things that sort of enter this analysis of the way how you estimate the distances, how you estimate the reddening, what relations do you use to estimate the absolute magnitudes or the distances. On the dynamical side, it also depends on how you evolve your orbits, which software do you use, which potentials do you use, how do you remove the stars that are just passing through, because the Milky Way bulge is a complex substructure where sort of a different populations meet. You have stars that are native to the galactic bulge, but you have stars that are just passing through. For all our stars, the majority of those interlooping stars are actually coming from the halo and from the disk. So there's a lot of ways how to do this, and there is not really one single right way how to do it. Now, in our work, we decided to do it with we sort of try to assemble the largest data set of irregular stars, for which we could put together their 6D information and combine it with their photometric metallicity. When I talk about 6D information, I'm talking about spatial properties, so we know where they are, and their velocities in all three directions. So we can have the detailed idea of where these stars are and roughly where they move from their orbits. So we combined different surveys that targeted the galactic bulge, in particular the RR Lyrae survey run by Andrea Kunder, which covers sort of a calcium triplet region. So if you use Gaia RVS spectra, that's basically the region that is covered by Brava RR star survey with a similar resolution. We combined also the data from the Apogee DR17, which observed many giants over the galactic bulge, and several thousands of them were actually irregular stars as well. Apogee operates in a different spectral region. It's more on the near infrared side, basically H-band if you work with photometry. So these spectra are usually low resolution, but still good enough to obtain some idea about the velocity. And then there is a little survey that was done using the VLT Flames Giraffe setup at ESO. So these spectra sort of allow you to estimate at least line of sight velocities to irregular stars in the galactic bulge. But that's not the information that you actually need. It's a one step toward that information. Because irregular stars are pulsating variables, so they change their temperature, radius with time. And with that, they change also their radial velocities throughout the pulsation cycle. And that means that the velocity that's sort of at the center of the mass velocity is convolved with the pulsation velocity, and you need to sort of correct for this motion using different techniques. The one that we used and that we actually developed prior this project works with the scaling relations and the line of sight velocity templates. These things can be developed if you have a well-populated sample of irregular stars that have covered fully the pulsation cycle with spectroscopic measurements, and then you can sort of create these templates and scaling relations. And it also depends which lines do you use, because the lines that you measure the radial velocity come from different depths. So the sort of the amplitude that you see on the upper panel sort of can change for different lines. If you use the Balmer lines, the amplitude is going to be larger because these lines originate usually in the upper levels of the atmosphere. While if you go for like iron lines, they usually originate from a deeper depths of the atmosphere. So we developed these tools, and then from the line of sight measurements that we have from the Brava and Apogee surveys, we corrected for this pulsation motion and obtained the actual systemic velocity. Now, when you have the 6D information on your data set, the spatial and the velocities, you can integrate the orbits in the analytic potential for the Milky Way that you choose to. We chose the one that is implemented in Agama, which is sort of based on a simulation and observation, both. And it contains not just the Milky Way disk, Milky Way halo, but also sort of a close to realistic our representation of the Milky Way bar, the supermassive black hole, and nuclear star disk and nuclear star cluster. In this sort of a analytical potential for the Milky Way, we integrated or evolved the RR Lyrae stars for which we had 6D information, obtained some orbital parameters. These orbital parameters, like apocentric distance, are important in order to separate stars that are sort of a native to the galactic bulge from those stars that are just passing through the interlooping stars. And one of the features, one of the parameters, the apocentric distance, has been sort of successfully used in the past to sort of identify these objects. In our case, we roughly found that in our sample, 22% are interlooping stars, while the rest is sort of a bulge native. But that sort of depends on the value that you choose to make the cut, and the literature estimates on these interlooping stars vary from 25 to 50%. It also depends on a lot of other things. I will get to that in this slide, actually. So we looked at from which regions of the Milky Way these interlooping stars are coming from. And we found that approximately 1 in 3 or 1 in 4 are actually coming from the disk. You can see it on the image on the right, where the stars that sort of are more on the metal-rich side, there is not that many of those that would have high excursion from the galactic plane. The Zmax represents in the orbit of a star that you evolve in the analytic potential, how high the star gets above the galactic plane. And the stars sort of that come from the metal-rich side of the metallicity distribution function for RR Lyrae stars in our dataset don't exhibit any high excursion from the plane. But if you look at the metal-poor side of this dataset, there's a lot of stars that get actually very high above the galactic plane and just live in the halo, but they are just coincidentally passing through the galactic bulge right now. And also the amount of interloopers that you can identify in your sample sort of depends on how close or how further you are from the galactic center. So this diagram completely on the left shows you basically galactocentric radius and how the amount of interloopers increases as a function of this radius. So further you are from the galactic center, the more likely it is that you actually observe a star that just passes through. We just didn't stop with the orbital parameters, but we also used orbital frequencies. Orbital frequencies are often used more on the simulation side, where you have individual particles for which you have their full orbits, and you can use Fourier transformation to decompose that into frequencies. So in principle, with the orbits that you have from the analytical potential for our stars, you have a function over time where you have either velocity or some positions on the vertical axis. So you can do the Fourier analysis and obtain the frequencies also for the observing data set. And these are really important if you want to sort of characterize the resonances and characterize the actual orbits of individual objects. So these are very, very useful if you want to study the galactic bulge. Now, basically, this panel is something that has been done in the past. We just made sure, sort of checked if it matches in our data set as well. It shows the rotation curve, these large panels, and dispersion curves in this slightly smaller panels as a function of metallicity. So we divided our data set into 6 metallicity bins and looked how the rotation curve and the dispersion curves changes with different metallicities. Now, the blue and red points represent 2 parts of the data set. The red points are the sort of the bulge native RR Lyrae stars, and the blue points represent the entire data set for that given metallicity bin. So we see that for the rotation curves, whether we remove the interlooping stars or not doesn't play that much of a role. That plays a role for the dispersion, where the dispersion, you basically by removing interlooping stars, you remove stars with higher velocities, so your dispersion decreases. So that's sort of an artificial fit here. By the way, the dashed lines represents sort of a dispersion and rotation curves that we would expect for the Milky Way. They come from the simulation. Now for the rotation curves, we found something that has been noticed already before, is that as you go from more metal-rich side toward more metal-poor, you start observing this kind of lag in rotation. It's like a decrease in the rotation velocities for these bin points. And when you move really towards the more metal-poor regime, that's where the rotation curve really sort of disappears from your data set. So this has been already noticed before, and we try to explore it, why this is happening for the earlier stars. We looked specifically in some of the orbital parameters. In the plot on the left here, on the horizontal axis, you have the apocentric distance. So that's the distance on the orbit, the furthest star gets on its orbit in the orbital integration. And the Zmax is again the excursion from the plane, so how high it gets above the plane. And we noticed that in the analytical potential that we integrated our orbits, it leads to this bifurcation, where the color coding I will get to that in a minute, but this bifurcation happens to sort of divide the stars into two categories, where the stars in the line of unity here, that sort of has the same excursion from the plane as the apocentric distance, do not show any, they sort of rotate retrogradely with respect to the galactic bar. That is shown by the color coding here with this orbital frequency, omega phi rod. So these stars sort of don't contribute to the bar itself, while the stars that fall below this line of unity have positive values of this omega phi rod frequency, which tells us that these stars are rotating progradely with respect to the galactic bar. And these are for earlier stars. There's this ratio between these two groups. Now, if we do the orbital analysis for the non-variable giants, like red giants in the galactic bulge, we again find this bifurcation again. Again, we have this on the line of unity stars that do not rotate progradely with the bar, so they are retrograde. And then you have this like a large population of stars that actually do rotate progradely, but the fraction is different. It's more likely to find a retrogradely moving earlier star than it is to find a retrogradely moving giant, a red giant, for example. And we sort of checked this using a simulation, N-body simulation of a evolved galaxy without any mergers or any kind of external effects, basically a secularly evolved galaxy, where again on the line of unity you see the stars, or the particles in this case, sort of move retrogradely with respect to the bar that is formed in the simulation, while below it are the stars that move progradely. Now the important thing is that the fraction between the retrograde and prograde is different for earlier stars than it is for giants. And that's what we explored next, basically in the plot on the left. Here, these points sort of represent the fraction of prograde versus retrograde as a function of metallicity. The blue squares are for earlier stars. The yellow points represent red giants from Apogee survey, and the pentagons represent blood clumps from BDBS survey. And you see there is this sort of like a bin distribution in the metallicity space. You see there's this like a linear progression that decreases the fraction of retrogradely moving stars as you increase the metallicity. So in principle, you can look at it as a progression with age. You can use the metallicity sort of as a proxy for age. That as you go from the oldest toward the youngest, you start seeing decrease in the retrograde fraction. And especially what stands out is there is still large error bar, are the metal-rich earlier stars in this regime that sort of behave kinematically different than their metal-poor counterparts. So we then looked also at another distribution that is binned again, but as a function of the retrograde moving stars with respect to the galactocentric radius. Again, the blue squares are earlier stars, and the red and the yellow points are red giants. And we see that this sort of retrograde fraction increases as you move closer to the galactic center. Now, if you would think that these sort of stars that do not support the galactic bar can originate in principle from some merger-driven evolution that they were sort of imported into the galactic bulge, you would expect them to be more on the, they would sort of show a little bit of a puffed distribution. They would be more a little bit on the further from the galactic center, but these ones are really deep in the potential, really like within half a kiloparsec to 1 kiloparsec from the black hole. So they are very deep in the Milky Way, galactic bulge, and they form sort of a spherical structure. And we see sort of this similar trend also with the simulation, That's where the simulation is, again, the galaxy evolved completely separately, secular. There's no merger, and it has a bar. It has similar features to Milky Way, and there you can see also that the fraction of retrograde moving stars increases as you go more closer to the center, and it also increases as a function of age, because in the simulation we have actually ages for individual stellar particles. So if you would take away anything from what I said so far, is that basically we created the largest data set of auroral stars with systemic velocities over the galactic bulge. We sort of confirmed the previously observed lag in the rotation, but we also noticed kind of newly that there's sort of a linear progression in the metallicity and the fraction of retrogradely moving stars. This allowed us, thanks to the frequencies, to sort of identify that as you move from the oldest over the youngest, in principle, in the metallicity space of stars in the galactic bulge, that this fraction of retrograde moving stars decreases. And these retrograde stars are more centrally concentrated than their prograde counterparts. And this sort of told us that spheroidal feature that was sometimes reported, that people often associated to the classical bulge, especially in the RR Lyrae community or in the metal poor side of regular non-variable stars, that Milky Way has some classical bulge. In principle, in our work, we showed that this doesn't necessarily need to be classical bulge, like a merger-driven formation, but we recovered similar trends with a completely secularly evolved simulated galaxy. So this spheroidal feature can sort of come out independently of any merger events that happened to the Milky Way. Now, what is missing here, what would be really good to have, is that whenever I talked about metallicities for large stars, I talked about photometric, and there is a kind of substantial error bar on individual measurements of these. And for the galactic bulge, what we are missing is a spectroscopic abundances. What we have so far is sort of a metallicity measurements either from photometry, which is with considerable error bar, or from some low resolution spectra for a small data set. And that's something that actually WST can change, can really make a huge contribution to bulge studies for auroral stars. Now I tried to do a sort of like a hand-wavy comparison with what WST can do for auroral stars in the bulge, and what Foremost, which is a new upcoming instrument, can do for that. Foremost is a visual focused and wavelength spectrograph with high and low resolution mode attached to a 4-meter class telescope, so smaller over in comparison to what the WST can do. It has a comparable sort of field of view, and I try to compare the high resolution spectrograph using the exposure time calculator for Foremost and WST using the same exposure, 1200 seconds, which is for auroral stars is roughly okay. Of course, for auroral stars, the problem with these surveys that you can face is that it's very difficult to co-add spectra to increase your signal to noise. So usually it's safer to use a single exposure and to sort of be fine with it to what kind of signal to noise you can get. I tried to use a similar sky and atmosphere, and what resulted from it is that while Foremost will sort of scrape just the outer region of the galactic bulge, WST can actually probe the galactic bulge error distribution with considerable depth. This signal to noise of 50 is roughly at 5,500 angstroms. So what the WST can do is provide high resolution spectra with a sufficient signal to noise for low tens of thousands of auroral stars, which would basically what we can do right now for solar neighborhood, we could do in much larger scale for galactic bulge, which would be wonderful, especially with the field of view that WST can have. Now, there's a sort of a competing instrument on that, which is called MOONS, which will start operations probably this year or maybe early next year. It's a high resolution multi-object spectrograph that should be attached to a VLT, and it sort of covers more infrared part of the spectral regime. So the high resolution should start around 7,500, 7,600 angstroms, so around oxygen triplet, and go towards 17,000 angstroms, so covering H band, so from I to H band. Especially in the H band, it will have a higher resolution, around 20,000, which should be sufficient to derive any abundances that you can find there. And the moons have the consortium have galactic and extragalactic survey, and the galactic survey will target the galactic bulge and galactic disk. It's called red wave. But in comparison to other large resolution multi-object spectrograph like Foremost, it is kind of like a smaller field of view, I think around 25 arc minutes. So all of these little green and red points that you see is basically they're targeting fields, and there's still a lot of stuff happening in between. And in comparison, this is the field of view from the Messenger article that they had in 2020, and this is where that field of view roughly lands with the data set that we studied in our work. And there's a lot of space between, a lot of space where a large survey can be done with WST. So the red wave survey will cover definitely some of the bulge irregular stars. They can provide some abundances there. But for me, I have no sense of how many abundances can be extracted from H band for irregular stars, because these stars are in general hotter than your general red giant star. So it might be a little bit more difficult to get the abundances that you would like to have from the H band. But that's a question for future. Well, this is all from me. Thank you for your attention. And if you have any questions, feel free to ask.
Thank you, Zdenek, for sharing your work with us. It's now time for questions, comments. Richard first.
Hey, Zdenek. Thanks a lot for a really nice presentation. I was wondering, I'm naive about this, or I don't know much about this. The increasing fraction of retrograde orbits when you go to younger stellar populations closer to the galactic center. Have you considered whether that might be due to resonant relaxation with the supermassive black hole near the center, or dark matter located there?
So that the fraction of retrograde moving stars is increasing with the galactic center radius. We didn't look at how close these stars get on their orbits toward supermassive black hole. It could be that. We didn't look into that. What we looked into was that in principle, when you have stars in this region, the galactic bar, it facilitates not just the distribution of gas, but also decrease of the angular momentum. So what we kind of saw in the simulation in our data set was that, or at least in the simulation mainly, was that some of the stars, like they lose the angular momentum and then they oscillate between retrograde and prograde. They just jump between back and forth. So there are
How
regions.
Can you tell that they oscillate?
In the simulation, because we have different time steps. So in the simulation, we could see that. In our observations, of course, we cannot, but we know that these the retrogradely concentrated the irregular stars, or general any stars, they are very retrograde and they are centrally concentrated. They have very little angular momentum, which of course, like it's not conserved in a non-asymmetric potential like the one that we have here. But in the simulation, you can see that there are regions in the galactic center where there's large regions where the stars lose the angular momentum, but there are some patches where they can gain a little bit. So it sort of bounces back and forth, back and forth. So these are probably the oldest ones that you can sort of find, or they had in general low angular momentum at the beginning.
Thanks. And if I may just ask a quick question about WST. So I appreciate the comparison of WST with Foremost and Moons. So to make sure that I get your points right, so the difference between WST and Foremost is, of course, depth. With Moons, it's aerial coverage, but you've also made a point of H-band and whether or not we can actually get sufficiently good abundances. So what would be the benefit here of WST versus Moons, or how does that stack up?
First, I'm not sure if I don't think I've seen a paper where people would try to analyze H-band spectroscopic data for irregular stars. There are some available, like if you look at the Apogee survey, there are some nearby irregular stars where you could try and test them. So my point would be that even that with WST you can do the similar depth, but you have the visual part of the visual part of the spectrum where you can have more lines, you can have more abundances, which for me would be more interesting because if I have only sort of an idea about metallicity, I would be happy to have some alpha abundances and especially neutron capture elements. I'm not sure how that would translate to H band for these kind of stars with these kind of temperatures. Maybe Valentina that has a question, maybe she has a more idea on this.
Okay.
Yeah, no, just a comment. Yes, we tried with Antonino Nunari, my PhD student, to get some chemical information using this apogee spectra for RR Lyrae, using the unstacked spectra though, so the signal noise is not great, as you know. Yes, I agree with the fact that there are major limitations in getting detailed abundances. So of course there is no hope to get any neutron capture element. And for what concerns the alpha element, yes, you are limited to magnesium and calcium, maybe. Maybe there are a couple of lines of silicon, but yes, it's not the right wavelength range for our Lyrae stars, I agree. And concerning instead, I have a question. What limiting magnitude have you considered when playing with WST ETC?
I used, I think, 15.5, 15.2, something like that.
Okay.
Of course, there's extinction and there is so for foremost ETC and for the WST ETC, I would like to have more freedom in choosing the conditions. And I don't know if the resolution of the high resolution spectrograph is settled yet for WST. It would be better if
yes. Well, Richard can confirm this. I think now it's set to 40,000, no?
Yes.
everywhere in all of those okay.
That's a good question. Whether the windows are all at 40,000, I don't recall at the moment.
So for the blue part, I understand why people go for blue part with higher resolution. Blue part, I mean around 4,000 angstroms. But if the resolution can be lower around 5,000, 5,500, that would be maybe better for this.
Yeah. I said this all the time also.
Yeah.
Yes, for us it's better. Thank you.
No, thank you for confirming what feeling I had about the H band.
Okay. Other questions, comments? Yes. Wang? Yep.
Yes, yeah. So you mentioned the mid-poor regions is the circular erosion of the Galactic bulge and the bar. So my question is then is it consistent with the thick bulge and long bar models?
I'm not really familiar with those models, so I cannot really comment on that.
I know. Yeah. So you don't agree then this is similar to the Galactic bulge, right?
Mm-hmm.
Some people, it seems that some people still think that it is more similar to this Galactic bulge. Could you comment to that? Yeah.
For me, the sort of what speaks against the classical bulge morphology. I mean, there is definitely a small part that I would maybe call a classical bulge there, but it's difficult to identify without sort of like some additional information on abundances, at least for me. And it's difficult to do it on an individual object side. For me, what speak against the classical bulge morphology in the general secular part that I have there, the spherical part of the star, is that they are very centrally concentrated. And that basically stars that have metallicities minus 0.5 or close to solar, they are also in that region. That they have they have retrograde orbits and they don't contribute to the bar. And I would not expect those stars to sort of come from a merger, but there's a small population of them there, but they are there. On the metal poor side, there's definitely an overlap. There's going to be definitely some stars that will be coming from mergers, and there will be some stars that originate from the secular evolution. But with the simulation, we sort of managed to recreate the trends with sort of a lonely evolved galaxy without any additional material to be accreted on that object.
Yeah, so there is still space for some mergers.
But I would say it's gonna be very, very like I'm sure that those objects are there. It's just going to be very difficult to identify them on the metal poor side, especially on a starburst type basis without particularly abundances. Like it would be great to have high detailed abundances on that. There was a paper by Denny Horta in 2021, I think, on the Heracles structure, or it was called Kraken by Diederik Kruisen in his paper 2019. And those stars are there. It's just there is much less of them, and I think that what people like associated for classical bulge among the earlier stars is that there's a lot of earlier stars in the classical bulge morphology, but I think that it's not the case. I think there is a portion of them, but much smaller.
Okay. The second one is then, so how when you handle the other real stars, how do you consider the volume completeness? There's some sky coverage, because other real stars is very old. Maybe there are some selection functions or some volume completeness and in different regions.
Yeah, that's true. There's definitely that in the surveys that covered the galactic bulge on the spectroscopic side. What we try to do when we for example compare it with the red giants or with other surveys non-variable stars is to have sort of the same footprint on the sky. That when we compared it with non-variable giants, that we sort of select them from the same distance region and from the same coordinates region. So we sort of compare at least like apples to apples in that regard. But yes, there is definitely a sort of a selection effect from the view that we have. But this is, I mean, Giulio has a question. He was the one who actually for the first time went above the galactic plane in his work. So now we are doing better than we did before, because before we were sort of staying below the galactic plane. Now we are also above the galactic plane. So we sort of don't have to assume that it's symmetric, but some selection effects there will be likely possible there.
Okay.
Yeah.
Okay, thank you.
Okay. Giulio first, then I have another question too. Giulio.
Ciao, Zdenek.
Hey.
Good to see you. Thanks for the talk. Well, great work so far in this. I was wondering about the ages, because you talk also that there is a relation between metallicity and ages, but limited to old ages in general, right? Because you know that there is now several new studies talking about this new mechanism to form RR Lyrae. So it would be interesting to for me if you can explain more how this is not happening in the batch, for example.
So I mean, I think that there's a connection between what we see in the solar neighborhood earlier stars to what we see for the metal rich. So on the metal rich side of earlier stars, there's a similarity what we see in the solar neighborhood and in the bulge. Basically, the metal rich earlier stars behave kinematically differently than in the solar neighborhood and in the galactic bulge. There's a difference between both populations. For ages, I don't think that there is a way. I mean, I know there is a way, but it would be very difficult. I mean, we would need ELT and ANDES to be operational and do that at least a little bit. But I think that it will be difficult to get age distribution. I mean, you can get age distribution for certain metallicity bins that has been done, I think, last year by Han Yang and collaborators, and basically the group at Cambridge. I think that can be done for the bulge as well. If somebody has a large data set of Meyer variables, they can do the same analysis and then compare the trends in the retrograde fraction. And then you can sort of, okay, for this metallicity, photometric metallicity for lower stars, we have these ages of Meyers, and then you can sort of do the same analysis that has been done on the solar neighborhood, but you can do it in the bulge, which I think would be, yeah, should be needed. And what I would really like to have is also alpha abundances for bulge or lower stars, but yeah, I need to wait for that a bit.
Thank you. I have a question, Zdenek.
Thanks.
Which reddening law did you assume in your analysis? And do variations in the extinction law affect your conclusions?
Yes. So we in our, I didn't talk about it, but there was a paper that we did the same year, but a couple months before, where we did basically the analysis of reddening and reddening law, and we derived our own reddening law, and we basically used our own derived reddening maps. We covered anything from visual to near infrared, and we showed there are differences in your results if you use visual or infrared. and we account that to variation in the reddening law on a large scale, actually, across the galactic bulge. And for this analysis, we in principle, what we do here is if we have a near infrared distances, then we use those. If we have visual distances, they have large error bars, and we use those as well. But we more take into account the ones that have like a K band or J band distances. So that's a big problem there. Yeah.
Okay, thank you. Other questions, comments? Okay, I think we can wrap up the session here. Thank you, Zdenek, and all of you for being with us today, and have a nice day, everyone. Bye.
Thank you for inviting. Bye-bye.
Bye-bye.
Thanks.
Ciao.
Ciao.
Ciao.